In this lecture, we derive an integral formula for the area of a region that is described using polar coordinates. The region, which is region A, is bounded by the graph of r equals r of theta, and the rays theta equals alpha and theta equals beta. Here, alpha and beta are between 0 and 2 pi, with alpha less than beta. To find an integral formula for the area of region A in polar coordinates, we first find a Riemann sum approximation for the area of region A. We partition the interval from alpha to beta. We start with theta sub 0, which we set equal to alpha. And then in a strictly increasing order, we have theta sub 1, followed by theta sub 2, and then theta sub 3, all the way to theta sub n minus 1, and finally we have theta sub n, which we set equal to beta. We should have n plus 1 partition points, or what we sometimes call nodes, and consequently, we should have n subintervals. The partition need not be uniform, and so a subinterval does not necessarily have the same length as any other subinterval. Let the index I go from 1 to n. We set delta sub I theta equal to the length of the ith theta subinterval. Then delta sub I theta equals theta sub I minus theta sub I minus 1. Let delta theta be the maximum length of all of the delta subintervals. As a consequence of the partition of the theta interval from alpha to beta, region A is also partitioned into slivers, one sliver for each theta subinterval. We don't expect the slivers to be very simple and regular geometric figures, and so there may not be a simple, easy general formula for the areas of the slivers. Besides, the term sliver is not a precise mathematical or geometric term. And so, in place of the slivers, we'll look for a regular geometric figure that comes with a simple area formula. Let us use pie-shaped regions, or what we call circular sectors. To get started, for the first subinterval between theta equals theta sub 0 and theta equals theta sub 1, we pick a random value of theta, which we call t sub 1, and then use r of t sub 1 as the radius of the first circular sector. We repeat this process for all the other slivers until each sliver is replaced by a circular sector. We now take a random circular sector. Suppose this sector is between theta equals theta sub I minus 1 and theta equals theta sub I. The central angle for this sector should be theta sub I minus theta sub I minus 1, which is equal to delta sub I theta. If t sub I is the random theta value between theta sub I minus 1 and theta sub I, the radius of the circular sector is r of t sub I. So we find the area of this sector using ratio and proportion. We start by constructing the circle whose radius is r of t sub I and whose center is the origin. We have already pointed out that the central angle for sector I is delta I theta. On the other hand, the whole circle corresponds to a full revolution. That means the central angle for the circle is 2 pi. Therefore, the area of sector I divided by the area inside the circle should be equal to delta sub I theta divided by 2 pi. The area of a circle, of course, is pi times the square of its radius, and the radius of our circle is r of t sub I. And therefore, the area of our circle is pi times the square of r of t sub I. And so solving for the area of sector I from this equation, we should get that the area of sector I is equal to half times the square of r of t sub I times delta sub I theta. The area of region A is approximated by the sum of the areas of all of these sectors. And so in summation form, the area of A is approximated by the sum from I equals 1 to n of half times the square of r of t sub I times delta sub I theta. Now this is a Riemann sum approximation for the area of A. We bring the factor 1/2 outside of the summation. If r equals r of theta is a continuous function on the closed interval from alpha to beta, and if delta theta, the maximum length of any theta subinterval, goes to 0, this approximation for the area of A should tend to a limit. The limit is equal to half times the integral from alpha to beta of the square of r of theta. Therefore, the area of A is equal to half times the integral from alpha to beta of the square of r of theta.